Let's look at a surface area computation. In this particular case, we're asked to compute the area of the surface f of x equals 64 plus x squared minus y squared that lies above this region. The region is x squared plus y squared less than or equal to 4. So that's basically this disk here of radius 2. Now what I've done here is I've gone ahead and labeled it in terms of polar coordinates. That is, this representation would just allow theta to run from 0 to 2 pi, and then of course r from 0 to 2, and hopefully we'll be able to make use of that. Now when we compute the area of a surface, when we have a Cartesian representation of the area, we need to look at the x partial of f and the y partial of f. These are very easy to compute. The x partial is just 2x, and the y partial is negative 2y. And then, of course, the argument for our radical is 1 plus fx squared plus fy squared. And so it's easy to square these. We get 1 plus 4x squared plus 4y squared, and then, of course, we factor the 4. And so now you can see why the polar coordinates might be useful here. So now surface area, now you can write S, uppercase S, or you can write SA, it's your choice. Sometimes I do SA, it does not matter. And we take the principal square root of this term, that is this expression here, and we integrate the double integral over R, this being our R. So in this particular case, we have a representation that is very well suited to polar coordinates, so we do a change of variable. So we move from Cartesian, which is represented by r, to the polar here. So we have theta from 0 to 2 pi, and we have r from 0 to 2. And then of course the area element dA from the change of variables is r d theta. And notice now this is nice and rigged for a calculus 1 integral because we have the r squared here and the r there. Notice again that these limits are constant, so we can break up the integral. The d theta integral is just from 0 to 2 pi. And then of course by the chain rule we're going to have an 8r here. So we're going to need an 8 here to pair with the r, and then we're going to need a 1/8 to pay for it. So this integral is just theta from 0 to 2 pi, which is 2 pi. And we have the 1/8 here that came along from the chain rule, and then by the power rule, add 1 divided by the new power. Our new power is 3/2. Division by 3/2 is multiplication by 2/3. So we end up with a very straightforward integral. Now at this point, notice we have a 2 pi times a 2, which is a 4 pi over 8. That reduces to pi over 2 times a third gives us pi over 6. And then, of course, by the fundamental theorem, we can substitute 2, and we get 1 plus 16 to the 3/2. And then, of course, substitute 0, we're just left with 1 to the 3/2. And then for your final answer, you can write the 3/2 power of 17 is 17 times root 17, if you like. Then we have the minus 1 all times pi over 6. And we are done.